Good afternoon everyone, and today I'm continue talking about growth of nanocrystals. But during sixth lecture I will talk about growing of nanocrystals not inside of the glass matrix, but in various organic matrices. I hope that you still remember that our main aim is to obtain monodisperse nanocrystals, and a fair way to accomplish it is to grow nanocrystals by chemical reactions in liquid, on micelle media, or in polymers. Here, matrix acts as a stabilizer, as well as it determines the chemical interface configuration and controls the size of nanocrystals via chemical equilibrium conditions. The growth of nanocrystals can be controlled by the choice of the solvent, the concentration of the reacting species, reaction temperature, and duration. Compared to glass technologies, this method has two advantages. First of all, it's low preparation temperature. Usually the preparation temperature in organic matrices are no more than 200 degrees Celsius. And second is the very narrow size distributions that we can obtain with the deviation of the mean size less than 5%. The most common methods to synthesis nanocrystals of type 2,6 are chemical preparation methods. Chemical replacement reactions are usually happened between chemical compounds providing metal ions and compounds containing chalcogenide ions, sulfur, selene, and tellure. The chemical reaction in general case can be written in this form. Here is the example of cadmium selenide. The synthesis is more often a two-step procedure, where during the first step cadmium salts or similar substances are dissolved in organic solvents, and during the second step oppositely charged sulfur or selene ions are added by the admixture of organometallic compounds based on the trimethylsilyl. By these methods we can obtain so-called superclusters of cadmium sulfur, stable and very small clusters that consist of 55 atoms. It's the smallest clusters that can be obtained by chemical methods and physical methods. A very convenient way to control the growth of the nanocrystals is to use a microheterogeneous media like reverse micelle media. It is a microemulsion where a small amount of water in a hydrocarbon solvent is surrounded by the surfactants. Surfactants are molecules having both hydrophobic and hydrophilic functional groups. I remind you that hydrophobicity is the property to repulse the water from the surface of the material, and hydrophilicity is a high wettability of the surface with water. Usually we use this micelle media, and in this micelle media the particle size is governed by the molar ratio of the water to the surfactant. Moreover, surfactants prevail the agglomeration of the semiconductor nanocrystals. In the figure, the cadmium selenide nanocrystal is demonstrated with the phenyl group on its surface. The selene atoms are added to the cadmium-rich nanocrystal via this reagent. Selene incorporates in the structure of the cadmium selenide nanocrystal, but the surface layer is replaced by a permanent chemical cap, owing to the strong bond between selene and carbon. One of the widespread techniques to obtain nearly monodisperse nanocrystals are sol-gel-based techniques. Sol-gel process is a method for producing solid materials from small molecules. The process involves the conversion of monomers into a colloidal solution, ZOL, that acts as the precursor of the integrated network, gel, of either discrete particles or network polymers. Typical precursors for this process are metal alkoxides. In our example, cadmium selenide nanocrystals have been stabilized by inorganic multifunctional ligands. These groups act both as the link to the semiconductor nanoclusters, covalently bonded via short inorganic chains, as well as AND groups incorporated into inorganic network. The nature of different stabilizing group strongly influences the electronic states that we can see at the absorption spectra. Here, the shift can be explained by different sizes of nanoclusters and stabilizers, and by different charge states at the interface between the amine-natured stabilizers, monoamine, diamine, and triamine groups, and cadmium-sulfur cluster salts. Large efforts are made to prepare highly monosparse nanocrystals, as you can see. A microheterogeneous environment already allows us a first control of the particle sizes, but we can go further. So we will discuss the two more ways towards the synthesis of nearly monodisperse nanocrystals: the gel electrophoresis and fast nucleation slow growth process. The gel electrophoresis is a post-preparative size selective method. It means that firstly we synthesize our nanocrystals, and after that we use gel electrophoresis. Here, nanocrystals are incorporated into a pillar of a suitable gel. An external electrical field is applied, resulting in a slow migration of nanocrystals. The velocity of the motion of the nanocrystals through the gel depends on the surface charge and the size of nanocrystals. Smallest particles first arrive at the lower end of the pillar, while larger particles are still in the middle. Gel is cut into small slices containing different sizes of nanocrystals. After that, particles from different slices can be dispersed in various solvents. And fast nucleation and slow growth process. Here we have the reduction of the nucleation process to a short time interval upon injection of room temperature reagents into a hot coordinating solvent. Here, a rapid increase of the supersaturation happens. And upon the sudden temperature drop and the fast decrease in the concentration of reagents, we obtain the fast nucleation. After this, moderator heating is used as the onset of the slow growth process. And simultaneously to this, the absorption spectra are used to monitor the changes of the size of the crystallets. Depending on what we want to obtain, growth temperature is adjusted to higher or lower values. Also, during this technique, surface of the nanocrystals is stabilized by the phosphine moieties connected to the alkyl groups. Stability of the system strongly depends on the interaction of the alkyl groups and with the solvent. So we decrease the concentration of the solvent by adding, for example, methanol, and the energy barrier for the flocculation, in other words, coalescence, lowers. Largest particles in the solvent have a higher probability of overcoming this barrier, so they coalescent, and by using gradual addition of the non-solvent results in a size-dependent flocculation that we can control, and how this we can further control the size distribution function and make it narrower. Cadmium selenide quantum dots that were obtained by this method with a mean size of 1.85 nanometers possess very narrow absorption lines on the absorption spectra because their deviation from the mean size in this case was less than 5%, and it is the lowest size distribution that can be obtained in the organic matrices. A third interesting development is the combination of different semiconductor nanocrystals by constructing the layered structures or by close contact of different semiconductors at the fragment of their interface. First structures are called sandwiches, and cadmium sulfur titanium oxide sandwich structure is a mixing of the two components in alkaline solution under high excess of cadmium ions. Here, the semiconductor with a smaller band gap, that is cadmium sulfur, absorbs the light. Absolute energy position of the lowest confined electron level is higher than the gap of the wide gap material, that is titanium oxide, and the lowest confined Hall state is situated within the band gap of the attached second semiconductor. So during this case we obtain the special charge separation of electrons and holes as a result of electron transfer processes. Then the second structure is called quantum dot quantum well. It is a free-layered structure which consists of a size-quantized cadmium sulfur nanocrystal as a core, surrounded by a complete layer of mercury sulfur on the surface, and covered again by a layer of cadmium sulfur at the outermost shell. Mercury sulfur here is the smallest band gap material with the band gap only 0.5 electron volts. It is embedded between the core and the outer shell of the material with the wider gap, cadmium sulfur, with a band gap of 2.5 electron volts. In this structure we have the core with the radius of 2.3 nanometers, then it stands the layer of mercury sulfur with a width of 0.3 nanometers, and the outer layer has the width of the 1.4 nanometers. Totally we have structure with the size of 8 nanometers. So, summarizing all the methods of growing nanocrystals inside of the organic matrices, we can point it out the next advantages. First of all, we have a variety of post-preparative size selection methods. We can achieve narrow size distribution. We have the possibility of charge transport, and also we can manipulate all these charges. But at the same time, we have several disadvantages. Nanocrystals grown in liquid environments are very unstable. They show photochemical reactions and they have to be protected against agglomeration all the time. Also, such techniques as surface capping and stabilization can prevent growth up to larger sizes. So, remembering the method of growing nanocrystals inside of the glass matrix, we should also bear in mind that glass matrices are very stable and robust. They are of a good optical quality and they are compatible with integrated optics, but at the same time we cannot obtain a narrow size distribution of nanocrystals. So the minimum size distribution that we can obtain is 10% and no more. Let's make a little synopsis of various techniques of production nanocrystals of different types. Here you can see nanocrystals of type 2, 6, that are cadmium sulfur, cadmium selenide, telluride, and so on. Most of all can be grown inside of the silicate and other glass matrices, polymers, and composite films. Nanocrystals of type 1/7, that are copper halides and silver halides, can be synthesized inside of the silicate and other glass matrices, inside of the crystal matrices with the same halide, and inside the organic solutions. Nanocrystals of type 3/5 can be mostly grown on their gallium arsenide surface and also in organic solutions and polymers. And the last most widespread semiconductors that are nanocrystals of group number 4, germanium and silicon, can be mostly grown based on the silicon oxide amorphous crystallite, silica glass, and silica glass composite films, and also porous silicon. This is the end of the lecture dedicated to the growth of nanocrystals. Thank you for your attention and goodbye.